So now we'll try to apply all of this to a real example, or a realistic example at any rate. So here we've got a system, a complex pipe system. It's a single pipe, but it has multiple diameters. There's a pump in the corner here. This pump is the bottom, and it's gonna be pumping water into this tank. And so it's gotta pump it up around this bend, and then around the second bend here. So I call this bend 1, and this is bend 2. The pipe has a diameter of, let's see, 3.5 centimeters right here coming out of the pump. And then after it makes the second bend, it goes through a sudden expansion to a larger diameter pipe of 8 centimeter diameter. It has a valve here, so you can control the flow. And at this, as drawn, it's a half open gate valve. So this valve is half open. And so that's going to restrict flow to a large degree. And then it's going to exit into the tank. And we know that the exit is also going to cause a recirculation and going to cause a loss factor as well. So we're going to have a loss coefficient for this bend, loss coefficient for this bend, a loss coefficient for the sudden expansion, a loss coefficient for the half open valve, and a loss coefficient for the exit. In addition, we have two lengths of pipe. We have 6 meters of pipe with diameter 1. That's going to have some frictional effects, obviously. And we have 10 meters of pipe of diameter 2. So we've got 6 meters of this first bit and then 10 meters of the second bit. All of that's going to add together to reduce the flow, or to try to prevent the flow. So we need a pump, and we're asked to find the power that's required to pump the water into the tank at a rate of 30 kilograms per second. So that's what we're going to do. We're going to try to figure out how to get this 30 kilogram per second mass flow rate into this tank, and how much power does that need. So we haven't really talked about pump power before. You may have seen it in thermo. I'm not really sure. But here's the formula for it. So this is a good one to write down where you can find it. This is how much power you need if you're going to use a pump. And so it depends on the pressure increase that the pump is going to create. So that's going to be pressure increase. In this case, it would be pressure out minus pressure in. At times the flow rate. So that's the volumetric flow rate. And if you look at that from a unit perspective, if you have trouble remembering it, of course your pressure increase is going to be in newtons per meter squared. Your volumetric flow rate is meters cubed per second. So that's going to come out to be newtons meters per second, which is joules per second. So that's watts. So this gives you the amount of watts you need to run this pump if you're going to, at the minimum. Of course, the pump may not be 100% efficient. But if 100% efficiency, this is the amount of power you would need to run this pump. Of course, because we have all these factors that are going to cause loss coefficients, we need a lot of loss coefficients. So here's 1. I say that bend 1K is equal to 0.6. The bend 2K is equal to 0.7. These are things you would look up on a table based on the diameter and the radius of curvature of the bends. This K for sudden expansion, well, we have a formula for that one. So I put down the formula here. This 1 minus little d squared over big D squared, all of that squared. That's your sudden expansion loss coefficient. For the half open gate, we have a 4 here. So that's a pretty big one, and we expected that to be big. And that's pulled off a graph. And so you see graphs that show gate valves for how open they are and the diameters of pipes. So there's about 4 in this case for a half open pipe at that half open gate valve at that diameter. And finally, we know that we're going to have this exit, and that's going to have a K of 1 because it's exiting into this water tank. So that's going to give us a 1. So I'm going to turn this video off now, and I encourage you to try to go back and look at the formula that we developed to calculate the pressure loss, or the pressure needs, for a pipe of this type, and see if you can actually apply this formula. So this is the formula that we learned before. Delta P plus rho G delta Z is equal to 1/2 rho times this group. So you have 2 different pipe diameters, so you have 2 different F's, 2 different L's, 2 different D's, 2 different U's, and then you're going to have these different loss coefficients, and they're each go with one or the other velocity. They're going to be 2 different velocities in this problem because they're 2 different pipe diameters. So some of the loss coefficients will go with one of the velocities, some will go with the other. You have to split them up appropriately, add them all up, and you get this delta P plus rho G delta Z. There is a delta Z here. The delta Z that we have been written is 5.4 meters. You could say, well, shouldn't we do it from the pump to the exit? And you could do that. But then you'd have to know what the pressure here is at the exit. So your delta P would be, instead of being from P naught to this pressure, it would be from whatever the pressure is here to this pressure. And I think if you think about it, you can see that it doesn't actually matter whether we go from the top to here and put that whole rho GZ in this term, or whether we go less high and then add rho GZ to this pressure, because that's what you add to this pressure to get from the top down to here. So it doesn't make any difference. The difference, the height that we're given is from the pump to the top of the tank. So that's a delta Z we have, and that means the pressure that we need from the pump is going to be the pressure increase above atmospheric pressure, basically the gauge pressure. So that's really, I think, the simpler way to think about it if you're given this height to the top of the tank. All right, so give that a try and see how it goes, and I will present the solution in the next lecture.